Okay, we're going to continue on here with chapter one, which we were talking about last time. So last time we got into really the atom, um, and we talked about some major sort of experiments that led to the better understanding of the atom. A lot of it, as we talked about, started with the CRT tube, which is our cathode ray tube. Remember, basically, two guys, important sort of experiments, Thomson, who used the CRT tube, and also Milligan, who did the oil drop experiment. Both of these sort of experiments helped us to have a better understanding of electrons and how they are sort of not really made, but sort of their properties. Electrons obviously was found to be negatively charged. Remember, Thomson was able to find the charge the mass of an electron, while Thomson, using his oil drop experiment, was able to figure out the charge of an electron, which allowed really sort of the mass of an electron to be sort of discovered. So from that, we were able to determine the mass of an electron from those two experiments, 9.09 times 10 to the minus 28 grams. At that point, it led, along with some other sort of experimentation, to really sort of the early model of the atom, which was the one that was proposed by Thomson, and that is the plum pudding model. And that is the model where the atom is basically all this positive charge sort of spread out over the sphere. It was believed, obviously, because electrons were present, that it has to contain something that was positive to balance out that negative charge. So we have that positive charge spread out all over the atom, with the electrons basically embedded inside. And the idea here was that most of the mass of the atom was made up of those electrons. So this was really the sort of understood idea of the atom until, again, the next major sort of experiment or discovery sort of happened, and that was our friend Rutherford. And he did that gold foil experiment. He did shoot alpha particles, which are these positively charged particles, at basically pieces of gold foil and other metals. Remember, based on sort of Thomson's model here of the plum pudding model, they expected these positively charged particles to kind of go through, and a little bit of deflection that was going to happen because we're shooting something that's positive. That's something that's positive and is moving really quickly. Remember that basically what they saw was they saw a majority of them pretty much sailed through with really no problem. Every now and then they would find our alpha particles being scattered at these large angles, maybe even coming back to the source. So what they had to sort of do is revise sort of this idea of the atom as being incorrect. And really, they came up with our modern sort of version of the atom, where the atom has a nucleus, and this has a very dense positive core. Later experiments found protons, which are positively charged, and also neutrons in 1930 or so, much later on, were found to be within the nucleus. They found that the electrons do move about in that empty space, and as we'll later find out, obviously, they do not move in pretty circles or anything like that. They do move really randomly about that empty space. The other major difference between sort of the earlier model and our modern day model is the idea that the most of the mass of the atom is actually made up of the nucleus. So the nucleus comprises most of the mass of the atom, and that is, as we will see, there are reasons for that. Any questions on any of that stuff we talked about, I think, last time? All right, so this is sort of where we left off, I think. This is just a summary table of a lot of the experiments that we talked about, leading us to understanding the atom. Our Thomson, our Milligan, and our Rutherford, and sort of what came out of each of those things. As we talked about, obviously, the presence of something that's positive was thought to be, and the protons were discovered to be in the nucleus and be positively charged. The protons have a mass of 1.67 times 10 to the minus 24 grams. which is about 1,840 times heavier than any electron. So if you remember, the electron mass is somewhere in the ballpark of 909 times 10 to the minus 28 grams. So this is much, much heavier than any electron that is flying around. And since it is positively charged and found in the nucleus, that also sort of backs up the idea that the nucleus where we find protons is a majority of the mass of the atom, again, as those protons are much heavier than an electron. At this stage, they sort of thought of the atom as the nucleus. Again, although it is the most massive part of the atom, it is the very smallest part of the atom. You can think of the atom as being like a big stadium, and like the nucleus is like a marble there on the 50-yard line, is sort of what it is. Protons are confined to the nucleus. Electrons are traveling out from some distance of the nucleus. There is some attractive forces between the protons and the electrons, as opposites attract between those two. So although the electrons are out of that nucleus traveling around in these sort of randomness, because of that opposite attraction there, it is going to be sort of tied to the nucleus, so it just doesn't sort of run away, if you will. It will feel some attraction to that nucleus, which will keep it sort of orbiting in that empty space. Again, not in pretty circles. They do move pretty randomly. Now, there's always sort of the idea that there was another subatomic particle in addition to protons and electrons, and it wasn't until about 1932 that James Chadwick discovered basically the existence of neutrons. And neutrons basically gave off energy very similar to X-rays and gamma rays, which have sort of no charge as well. We talked about a few different types of radioactive particles that were used in a lot of these experiments. We had alpha particles, which are positively charged radioactive particles. We have beta particles, which are really negatively charged particles. And we have gamma rays, which is basically have things that have no charge. So a neutron is 1.67495 times 10 to the minus 24, which would also put the neutron about 1,840 times heavier than any electron that is flying around. So because both the proton and the neutrons are found in the nucleus, they're both about 1,840 times heavier than any electron. That again leads even more sort of credibility to the idea that most of the mass of the atom is really made up of that nucleus rather than the electrons, which are flying around. Out of those three particles, the protons, the neutrons, and the electrons, it is the neutrons which are actually the heaviest of all of them. They just slightly beat out the proton. They're fairly close to each other, which is why they go to so many digits on each of those numbers. So in terms of the most massive or heaviest particle, it is the neutron, followed very closely by the proton, and the electron is the lightest of those particles. Any questions on that there? So you do need to know the particles. Obviously, you need to know their charges. You need to know where they're found in the atom. And you don't necessarily need to know the actual masses of each of them, but you do need to know that the neutron is the heaviest, the electron is the lightest, and obviously the proton is second heaviest out of all of them. Any questions on any of that there? All right, so again, location-wise, electrons moving around the nucleus in odd patterns, sometimes referred to as Heisenberg's uncertainty principle. We'll talk a little bit about it in the next chapter, but the idea there is at no given time for a particle like an electron, will you know exactly where it is and how it's traveling. And again, more you know about its location, the less you know about how it's traveling, and vice versa. When you look at protons, neutrons, again found in the nucleus, comprising most of the mass of our atom. And there's sort of a graphic saying this is electron density sort of map, and sort of see it, I guess. The darker area here is a higher probability of finding electrons, and as you sort of fan out, it gets a little bit lighter. and less of a probability of finding electrons. So you can see there the nucleus is relatively small in size, but it is, again, the areas where most massive, and we do see the highest probability of finding electrons is near that positive nucleus. And again, because of the opposites attract, there's going to be that attractive force between them. So the chemistry of atoms really do come from electrons. In normal chemical reactions, that's pretty much all that's involved are electrons. In a normal chemical reaction, pretty much all that happens is we break apart all the bonds on the reactant side. They basically reassemble on the product side. We don't lose any elements along the way because really all we're really playing with are electrons. So let's talk about some other important aspects of an atom, which is the atomic number, the mass number, and what isotopes are. So we will start with isotopes. Isotopes, if you remember, are, bless you, basically the same element, but they have different masses. And because they have different masses, they basically have different numbers of neutrons. So this is one of the reasons, sort of the discovery of isotopes, like we talked about, is one of the reasons why one part of Dalton's atomic theory that we talked about last time is incorrect. Again, that part where he said the atoms of the same element are pretty much identical to each other. So these are, again, the same element, but they are different as they have different numbers of neutrons and different masses, so they won't be identical to each other. The good news is neutrons and protons really do not participate in normal chemical reactions, which we talk about in this class. When you go to 200B, we'll talk about nuclear chemistry, and they all basically involve neutrons and protons. So it's a very different sort of type of reaction than a chemical reaction. In nature, most elements have some naturally occurring isotopes that occur. These are actually two isotopes of sodium, that's sodium-23 and sodium-24. The difference here is they both have 11 protons, and one has 12 neutrons and one has 13 neutrons. So they are what are referred to as being isotopes of each other. So one really important number is the atomic number. The atomic number is Z, and that is the definition of atomic number is the number of protons that you find in the nucleus of an atom. Now, if you happen to have a neutral atom that is present, because there's really only three types of particles in an atom, protons, electrons, and neutrons, the atomic number will also tell you the number of electrons if it is neutral. There should be a very important point to that, which is if you are asked a straight up question of what is the definition of the atomic number, the definition is just the number of protons. So that is the official definition of the atomic number. Sort of the number that you could get from that is, again, if it is neutral, it will also tell you the number of electrons that are present, so everything balances out. But the actual definition is just protons. The chemical identity can be determined by the atomic number. If we go to the periodic table, we will find the atomic number sitting right there. Typically, that is the number up on top of the element on the periodic table. So if you look at a periodic table and look at all the numbers that are up there on top, you will see that no number repeats. Yes, they're all different. Every element has a unique atomic number, which means it has a unique number of protons, which means the number of protons is the most important thing in terms of knowing what element you are dealing with. And that's what we actually see here on the previous slide. If we look at the sodium, they both have 11 protons, and that's because sodium has 11 protons, and that's what makes it sodium, not the number of neutrons. So if you ever know the atomic number, or you know the number of protons, which is essentially the same thing, you'll know exactly what element you're dealing with. If you are ever given the number of protons or the atomic number, you could simply go to the periodic table and find the atomic number that matches, and you'll know what element that you are dealing with. So for example, there, nitrogen, if we looked at it there on the periodic table, it's going to have a 7 above it, which is its atomic number. And that means that if we had a neutral nitrogen atom, it would have 7 protons, which are positive, and because it's neutral, and we know it has no charge written there, it would also have to have a matching 7 electrons to give us basically no overall charge. So again, if it's neutral, you'll know also the number of electrons that are present. Any questions on that there? Another important number is actually the mass number, and the mass number is the number of protons and the number of neutrons that you find in an atom. Is sometimes abbreviated as an A. So the mass number is both the number of protons plus the number of neutrons. And that's important because if we take our atomic number that we just talked about, which is the number of protons, and if we subtract those two things, you can use both of those numbers to figure out the number of neutrons that are present. So if you take the mass number minus the atomic number, that will tell you the number of neutrons that are present. Pretty much all atoms will have protons, electrons, and neutrons. The exception is hydrogen. Hydrogen has a proton, it has an electron, it does not have a neutron. So everybody else will have all 3, but hydrogen just has those 2 that are present. When you are calculating the number of protons, electrons, neutrons, the mass number, atomic number, they all should be positive whole numbers. Okay. So the question is, when I go to the periodic table and I look at it, can I find the mass number on the periodic table? The answer is no. Yeah. A lot of people go, that's the mass number right there. That is not the mass number. That is the atomic mass. Yeah. Sometimes the molar mass, but that is the atomic mass. It is not the mass number. So you cannot find the mass number on the periodic table. Easy way to remember that is it needs to be a whole number. So if you look at the bottom number on a periodic table, they're pretty much all decimals. They're not whole numbers. So that's a good way to remember it. What confuses people sometimes is the mass number and the number you see on the periodic table. They're kind of like very close numbers in a lot of cases. So it is not that number. It is different. That number up there is actually found differently. It is found by taking the average mass of all the naturally occurring isotopes for a particular element. It's actually how that number comes about, and it is not the same as the mass number. So do not be the person on the exam that uses that as the mass number. Yes. So if you see yourself writing some decimals next to mass number, just put an X on it for me. Yeah, make it easier to grade and all that kind of stuff. Any questions on that? Yeah. So isotopes, as I mentioned before, they have really different numbers of neutrons, which is why they do have different masses. So these are actually 3 versions of hydrogen. Hydrogen has 1 proton, no neutrons. Deuterium, which is sometimes referred to as heavy hydrogen, has 1 proton and 1 neutron. And tritium, which is kind of like the radioactive version there of hydrogen, has 1 proton and 2 neutrons. These are all isotopes of each other. They are all hydrogen in its essence. Sometimes a very common way that we write symbols with mass numbers and atomic numbers there is we put the symbol from the periodic table. Top left of the symbol, we'd use the mass number. Bottom left there is the atomic number. So that's a very common way to do it. Another very common way is something like this, like Cu-64. 64 is mass number, atomic number. What do we think? That is well, I know I could find the atomic number by going to the periodic table and looking at copper, and above copper it says 20. I really can't see it, but I'm gonna go with 29. Hopefully they haven't changed it after all these years. That's still 29 over there. So that is 29, which would be its atomic number. So that's definitely the atomic number, which means by default here, that 64 is actually the mass number. So that's another very common way that isotopes are written, symbol dash a number, that number being the mass number, or again, mass number on top, atomic number on the bottom. So if we were to write the symbol for each of these isotopes of hydrogen, we would look at what was given to us: 1 proton, no neutrons. So if you didn't know what hydrogen symbol was, all you have to do is go to the periodic table and find number 1, and you would see that that is hydrogen. And we would put the atomic number in the bottom left, and the mass number would be protons and neutrons added, which in this case would be 1. So that would be the symbol there for hydrogen. If we were going to do it for deuterium, deuterium doesn't sound like hydrogen, but it tells us it has 1 proton, which means its atomic number is 1. And if I go to the periodic table, I'm still going to see our friend hydrogen there as our number 1 there. And our mass number would be these guys added together, which would be 2. So that would be the proper symbol there for deuterium. And lastly, for tritium, once again, maybe doesn't sound like hydrogen, but because it has 1 proton, it has an atomic number 1, which means its symbol is still going to be 1. And 1 plus 2 gives us a mass number there of 3. So as you can see here, it is the protons, which is the most important. It is the one that determines the element that you're dealing with. If you change the protons, you change what element you're dealing with. You will never have a carbon atom with 3 protons, because those with 3 protons should be what type of atom? Should be lithium. Yeah, so lithium is the only one that should have 3. Any questions on that? That is also why when we have a chemical reaction, we have the conservation of the elements, because all we are changing are electrons. So we would only change the elements if we change the protons that are happening there, and that doesn't happen in a chemical reaction. Just the bonds and electrons basically change. Any questions on any of those there? Yeah. All right, so take a second here for each of these. How many protons, electrons, and neutrons we got going on? Yeah.
So the table up there.
Yeah.
Does it tell us the atomic mass, right?
Sitting on the table up there, it does tell you the atomic mass. That's actually the number on the bottom. It doesn't tell you the mass number, if that's your question.
Mass number had to be 84.
Yeah, everything that you calculate in terms of these things, mass number, atomic number, number of protons, electrons, and neutrons, they all have to be whole numbers. Yeah. So that's why a good way to remember that number on the periodic table is not the mass number, is pretty much all of them are decimals, right? So they're not all whole numbers for sure. So that's a good way to remember not to use it in this situation. Yeah. What's that? You would have to figure out, depending on what isotope of carbon you're talking about. So in these type of problems, you would have enough information given to you to either figure out the mass number or figure out the number of neutrons that you have. Yeah. So let's take a look at these here. So an earlier question was, are we assuming that these things do not have a charge? And that's what we're going to assume here, since we do have the symbol. And in most cases, if something did have a charge, that's pretty much where you would see it, right? So you would see something like a plus or a minus, and we don't see anything here. So we can assume that it is neutral. So a reminder again that when it is written like this, our top number here is our mass number. Our bottom number here is our atomic number. And again, the definition of the atomic number is the number of protons that are present. That would mean this CO, which is cobalt. The number of protons in this case would be 27, which basically are 27 positively charged things. Because this is neutral, that would also tell us, because the only thing that is negatively charged in the atom is electrons, we would also need to have 27 electrons, right, to balance it out. So the number of electrons in this case would be the same, which would be 27. That will give us no overall charge, basically, right? They balance each other out. Our number of neutrons in this case will be our mass number, which is 60, minus our atomic number, which is 27. I can go without the calculator and go with 33 and hope for the best. Yeah, so that is 33 neutrons that we got going on there. Any questions on that there? Looking at the next one here, that is chlorine. And once again, we don't see anything written here, so it has no charge. So looking at our atomic number first, which will tell us our number of protons. Our number of protons in this case would be 17. Once again, to balance the 17 positive charges that we have, we would have to have an equal number of negative electrons, which would give us 17 once again. That will give you an overall charge of 0 in that particular atom. Our number of neutrons in this case, going to do 37, which is our mass number, minus 17. And we'll go with 20 on that one. Yeah. And lastly here, U, which is uranium, I think. I think they fixed that in the lab manual years ago on that periodic table. They had the wrong name on that, but they might have fixed it. 92 is our number of protons. Once again here, no charge, so our number of electrons will match in this case, giving us once again that no charge. And 238 minus 92 should be our number of neutrons. Feels like a big number there of like 146. Hope so. Yeah. So any questions on any of those there? All right, then let's take a look at a few more here. All right, so for each of these, let's write the symbol with this mass number and atomic number based on the information. Okay, let's take a look and see. So we'll start with krypton. So if we go to the periodic table, krypton there is 36. And again, that 36 on top is going to be its atomic number, which means we should put that on the bottom. Here we do have the neutrons given to us, so the atomic number is also the protons. So our mass number will be 48 plus a 36, right, to get to our mass number. And that's going to get us 84, which would go up on top, right? Any questions on that one there? Looking at nitrogen, which is N on the periodic table. If we go to periodic table, we will see a 7 written above it, which is its atomic number. And that means that we should put a 7 on the bottom. That also, again, is the number of protons. So our mass number here will be 6 plus 7, right? Will equal our mass number. And that's going to be a 13 up on top. And lastly here, if we take a look at iron, looks like 26 over there is iron, which is Fe. Once again, that is going to be our atomic number, which is our number of protons. So we will have Fe 26. In this case, they actually gave us the mass number, which is 56. That would tell us for this iron, in terms of number of protons, we do have 26. It is neutral, which means the number of electrons would be 26, again, giving us no charge. And our number of neutrons in this case would be our 56 mass number minus our 26, which is our atomic number, which would be 30 in this case. Any questions on any of those? Questions on how to do mass number, atomic number, protons, electrons, neutrons? Now, what happens if we did have something that did have a charge? How does that sort of affect it? So let's take a couple of these examples here that we have. So obviously in this case, for this nitrogen, we have protons 7. We have electrons would be 7. And that gives us no charge. And our number of neutrons here would be our 6, which is our 13, obviously minus 7, which is 6. So if we had, say, a nitrogen that did have a charge, like a -3, and we had something like this and like this, the number of protons in this one would be, number of protons here would still be 7, right? And it really won't change because it's still nitrogen, right? So we can't change it. Number of electrons in this case is going to be, it is going to be 10 electrons. So 10 negatives plus 7 positives leaves you a -3 left over, right? And that is where the charge comes from, the number of electrons. Number of neutrons here will be the same in this case, right? Because they both have that. So in this particular case, that has a negative charge, and it is only the number of electrons that has changed. If we look at iron, for example, here, and we had a +2 charge, our number of protons here will again still be 26 because it is iron. Our number of electrons here would be 24. 26 positives, 24 negatives leaves us a +2 left over, right? And again, that is where the charge comes from. And again, here, our number of neutrons in this case would be the same. So these are two things that have charges, and things that have charges are what are referred to as being ions, right? These are things with charges. And there are two types. There are cations, which have positive charges. There are anions, which have negative charges. And we can see really the difference here when we compare between the neutral nitrogen and the nitrogen with a -3 charge. The only difference is the number of electrons, and it actually gained electrons, right? And that's why it has a negative charge. It has more electrons than protons at this point. The charge that we see here tells us these things. The negative tells us that it gained electrons, and the 3 tells us it gained 3 electrons from its neutral, basically, self. So anions are things that gain electrons. And when we look at the iron versus the iron with a +2 charge, the only difference, again, here is our number of electrons. And in this case, it actually has 2 less electrons than what it started with in its neutral. And that is a cation. It basically has lost electrons. When things lose electrons, they have more protons than electrons, right? And they become positively charged. And again, same thing with the charge here. The 2 tells us it has lost 2 electrons. The positive tells us it lost electrons, and 2 is how many it lost. So if something does gain a charge, either positive or negative, really the only thing that changes is the number of electrons. A good way to remember that is you cannot change the protons, because as we've been talking about, if you change protons, and no longer it's the same element, right? So the only thing that could change is the electrons, and neutrons have no charge, so it can't affect the overall charge. So it really is just the electrons that affect the charge on something. Any questions on that there? So if I had something like how many protons, electrons, and neutrons does this guy have? And let's do and how many protons, electrons, and neutrons does this one have here? Okay, so let's take a look at the first one. So in this case, the number of protons here should be 29, which is the atomic number there for copper. In this particular case, it does have a +1 charge. So the positive automatically tells us it has lost an electron and has lost 1 electron. And in a neutral situation, that should have 29 electrons, right? So since it lost 1 electron, it needs to have only 28 in this case, right? Which gives us our +1 charge that we see. In terms of our neutrons, our number of neutrons in this case would be 64 minus 29, going to be 35 in that case. Any questions on that one there? Here with oxygen, our number of protons going to be 6. In this case, we see a negative charge, which means it has gained electrons. We see a -2 charge, which means it has gained 2 electrons from its neutral self. This neutral self would have 6 electrons, which means the number of electrons in this case would then need to be 2 more, which would be 8. That's going to give us 6 positives, 8 negatives, and our -2 charge sort of left over. And our number of neutrons in this case, 12 minus 6, which is 6 in this case, in terms of our number of neutrons. Any questions on protons, electrons, neutrons, things with charges, ions? Yeah. What's that? Yeah, they can. So even a sometimes we think of isotopes as like being radioactive per se, but they're not all radioactive. So yeah, it can. So the neutral isotope of an element can lose and get electrons. Other questions? All right, so we're not going to talk too much about energy, but energy again is usually used as the ability to do some type of work. We talked about the law of conservation of energy, I think, a little bit earlier on. Again, we do not lose energy along the way. There's sort of this perfect exchange of energy, as we talked about. So whenever somebody loses a certain amount of energy, somebody else will gain a certain amount of energy. We talked about really two types of situations: exothermic, that's when energy is released. And remember that essentially those are going to be negative sort of values if you have a calculated value of energy given to you. Endothermic is when energy is absorbed. And those usually result in positive sort of values. So again, if something gives off like negative 500 kilojoules of energy, the surroundings will pick up. Whatever's near it will pick up the 500 joules of energy, kilojoules of energy. It would just be positive for surroundings because it's absorbing the energy. It would be a negative number for the system that's releasing the energy in that sense. Heat does flow, by the way, from hot to cold, right? So things that are hotter cool down, right? Things that are colder cool, warm up a little bit along the way. There's different types of energy. There's radiant energy. There's thermal energy, which is really associated with the number of particles that are present. So thermal energy and temperature is a little bit different. They are not exactly the same thing. Temperature is usually a measure of sort of the energy that's sort of happening, but something like thermal energy is related to the number of particles and molecules that are present. So for example, if you had a bathtub of water at 40 degrees and you had a coffee cup at 80 degrees, it is the bathtub that actually has more thermal energy because the bathtub contains a lot more molecules moving around. That's going to cause that. The coffee cup has less thermal energy, but it has a higher temperature because in the coffee cup there's less volume, right? So it takes less energy to raise the temperature of a substance. So in that smaller amount, it may represent a higher temperature value. While if you have a whole body of water there, it's going to take a lot more energy to move the temperature digit 1 degrees. That's what sometimes referred to specific heat capacity, right? The energy required to move substance, 1 gram of a substance by 1 degree Celsius. So the higher the specific heat capacity, more energy is needed just to see a very small temperature change of 1 degree Celsius. Water, for example, has a very high specific heat capacity, which again is why people get really nervous when even the water temperature just moves a little bit like the ocean temperature, because the amount of energy required to change it just a little bit of temperature is a super amount of energy to do that because it has a very high specific heat capacity. Sometimes people go, well, it's only like a slightly change in temperature. It's not a giant change, but it takes an enormous amount of energy to change that body of water that much by temperature. Chemical energy, there's energy stored within bonds. So when we make and break bonds, there's lots of energy change that occurs. When I make a bond, do I have to put energy in or remove energy to make a bond? When I make a bond, I need to remove energy, release energy as an exothermic process. If you think about it, you got everybody moving around, right? When you release the energy, they could kind of slow down and come together to make the bond. When you have a bond and you want to break it, you got to put energy in there. When you do, they gain energy and they wiggle away from each other. That's exactly how it does not happen, but then they gain energy and they basically have enough energy basically to break apart. So we can figure out the change in energy in a reaction solely by looking in a reaction how many bonds are broken versus how many bonds are made and the energy difference that occurs. Nuclear energy is energy stored with protons and neutrons. When you get into that nucleus, there's a big energy change that occurs. There's also a little bit of mass as it changes, gets converted into energy. That's why radioactivity happens a lot, like when we use nuclear power and things are radioactive and has a lot of energy coming off. Potential energy, right, is that energy based on its position, right? And again, the classic example is the big giant rock on top of the boulder or the hill has a certain potential energy, right? As it falls, it can turn to kinetic energy. As it lands, it will have new potential energy from where it started. It will also transfer that energy to the ground as well. Some important units of energy are joules, and an important relationship that we do see along our way here is a joule is the same thing as a kilogram, meter squared, second squared. So we do see that relationship. We'll see it in the next chapter, actually. So that's a good thing to keep in mind. But joules and kilojoules is a very common unit of energy that is used. Also, calories is also another very common unit of energy, and that is lowercase calories. There's also capital calories. Capital calories are nutritional calories, like in nutrition. 1,000 of the little calories, little c's, is equal to one of the big c's, which is also sometimes referred to as a kilocalorie, right? And those are common units. So calories and joules are very common units of energy that we come across, in kilojoules and kilocalories. Most of the time in chemistry, joules and kilojoules are going to be your sort of energy unit that you see the most. Other things like pounds per square inch and some other ones, are not bar, but pounds per square inch is used for energy as well. So a reminder, we don't really officially talk about energy in this class, but things like energy do pop up in other chapters because, again, they assume that she did that. Any questions on that there? All right, so that is chapter 1. We're going to roll into chapter 2 here now, I think, if I can find it. We're going to talk a little bit more about the atom, and really we're going to talk about mainly electrons. And a lot of what we're going to talk about in the chapter, we're going to talk about electron configuration, talk about quantum numbers. We're going to talk about the idea of electrons transitioning from one energy level to the next. And towards the end there, I think we'll hit the periodic table and all that good stuff. So fireworks there, as we see, and as we talked about the other day, we're going to do a flame test, and very similar to what we'll do today. A lot of what we will be looking at in this chapter is the idea of, again, we have electrons, if that arrow represents an electron, on a specific energy level. And maybe something is done to it to excite it to a higher energy level. And again, as we talked about, what's going to want to happen is going to want to work its way back down to sort of a lower state of energy. Because we do have that conservation of energy, the atom itself does need to release that energy, right, in order to allow the electrons basically to relax back down. Just like the atom itself had to absorb some energy to allow the electrons basically to jump from a lower energy level to a higher, like when you took your wire, and just your wire, not the entire thing, into the fire, and you excited the electrons in that sample, just like you'll do today when you turn on the lamp and it gets an electrical charge. It's going to excite all the electrons to go to a higher energy level. So that's going to allow the energy, again, to basically be given off in the form of a wave. And as we'll talk about, we talked about a little bit last time, again, depending on what the wavelength of light that's coming off, it may come off in the visible part of the spectrum where we do see colors. Again, may come off in a different part of the spectrum where you might not see colors. Maybe you'll may feel something like heat or energy sort of coming off as a result of it. That, again, is why we do see our sort of firework colors. Again, they have different elements, so as they explode, they gain a ton of energy, and as those electrons start relaxing back down, which happens very quickly, again, you see the different colors in that visible part of the spectrum. So electromagnetic radiation, which is basically how energy is basically moved through space, it does move in the form of waves. And when we talk about a wave, there are several characteristics of a wave. There is the wavelength, which is between two peaks or two troughs there, this way. There's also the frequency of a wave, which is basically how many times in a second a wave passes a particular point. And there's the speed of a wave, which again is basically how fast that particular wave is moving. There it is. So this is our wavelength, which is sometimes abbreviated with the lambda symbol. And that is our frequency, which is actually the new symbol, not really a V, although most people call it a V, but it's not really a V. And that, again, is the number of waves that happen per second. Typically speaking, the units of wavelength a lot of times will be meters. Typically speaking, the unit of frequency is reciprocal seconds, or a hertz. A hertz is the same as a reciprocal second. A reciprocal second is 1/seconds is the units. And the speed of light, I personally used a rounded number. So you'll see me use 3 × 10⁸ meters per second. this uses that. I think your lab manual might also use like that 2 point whatever number. I personally rounded up there to 3 times 10 to the 8 meters per second. This is important relationship. If you take the speed of light, it will equal the wavelength times the frequency. The speed of light is usually in meters per second, which means the units of wavelength is meters. The units of frequency is reciprocal seconds, which is 1/seconds. And that is how we get 2 meters over seconds here. So that means that if I want to solve for the wavelength, that is the speed of light divided by the frequency. That also means that if I want to solve for the frequency, that is the speed of light divided by the wavelength in this case. So you want to make sure for sure that you are using your exponent button when you punch these things into your calculator. Once again, that is your EE button. Otherwise, you will end up with the wrong answer. Any questions on that there? All right, so why don't we try one here? Maybe what is the wavelength of red light that has a frequency of 4.62 times 10 to the 14? And let's do it in nanometers. So what is the wavelength in nanometers? Nano is like 10 to the -9. So see what you come up with. All right, so let's take a look. We'll use our C is equal to our wavelength times our frequency. In this case, we are given the frequency of 4.62 times 10 to the 14 reciprocal seconds. We are looking for the wavelength here, and the speed of light is a constant, which is 3 times 10 to the 8 meters per second. So rearranging our equation to solve for wavelength, it is C divided by the frequency. Putting in here our 3 times 10 to the 8 meters per second divided by our frequency of 4.62 times 10 to the 14 reciprocal seconds. The seconds will cancel each other out, and we will be left with meters at this point. Remember, we want to use our exponent button, which is 3 exponent button 8 divided by 4.62 exponent button 14. That is going to get us an answer of 6.49 times 10 to the -7. Once again, this will be meters. First off, any questions on that so far? Now we do want nanometers. So nano is 10 to the -9. That means that in one of the prefix units, there's 10 to the -9 of the base unit, which is a meter. So if we were to do that as a conversion, 6.49 times 10 to the -7 meters. On the bottom would be 10 to the -9 meters is 1 nanometer up on top so that the meters cancel. We're going to basically divide this by 1 times 10 to the -9. And it would probably help to punch it in correctly when we try that again there. There we go. That's going to give us 649 nanometers in this case. Any questions on that calculation there? So again, if you find your answer looks good here, but not so good there, it's probably how you are punching it into your calculator. You're not using your exponent button correctly. Yeah. All right, let's try another one here, maybe. Calculate the wavelength of red light. That is the one right there we just did. Hopefully they agree. Let's do this one. Calculate the wavelength of a radio signal that has a frequency of 100.7 megahertz. Yeah. Mega is 10 to the 6. Yeah. All right, so take a moment there, see what you come up with. We could do this one in meters, is good. We'll look for the wavelength here in meters, is okay. Okay, so looking at this one, once again, we're going to use our equation here. Our C is equal to our wavelength times our frequency. In this case, we have a frequency of 100.7 megahertz. We are again looking for the wavelength. And once again, we do have C, which is this. I'm going to convert this into a more usable unit of frequency. So I'm going to take 100.7 megahertz It says mega is 10 to the 6. That would mean in one of the prefix units, which is megahertz, there would be 10 to the 6 hertz, which is 1 times 10 to the 6. So again, that is the correct way to use that conversion. Doing that here, we're going to take 1 megahertz, 10 to the 6 hertz. And that will get us 100.7 times basically 1 times 10 to the 6. That's going to give us 1.007 times 10 to the 8 hertz. Since a hertz is the same as a reciprocal second, that would give us 1.007 times 10 to the 8 reciprocal seconds. Again, it's a 1-to-1 conversion between those two. Any questions on that there? Now that we have that, we'll once again rearrange our equation and solve for the wavelength, which is c divided by frequency. We're going to do 3 times 10 to the 8 meters per second. 1.007 times 10 to the 8 reciprocal seconds. Seconds here will again cancel and leave us with meters. So that is going to get us something like 2.98 meters, which is about what you see in the radio wave area of the electromagnetic spectrum. Question on that one there. So you do need to be obviously know this equation, you need to be able to calculate obviously the wavelengths, frequency. Again, that nano conversion is a very common one that we see a lot. A lot of the visible part of the spectrum where we see colors, they are usually given in nanometers as sort of the typical wavelength that they're given. Other wavelengths are usually given in meters, is very commonly given that way. Any questions on any of those calculations there? All right, so hopefully it agrees with us. That's good. All right, so when we talk about waves, there is a relationship between waves, their frequency, and the energy associated with them. So as we might talk about in the last lab, if we have a much longer wavelength, we have typically a long wavelength. That usually will mean we have a lower frequency, and that usually is a lower energy associated with that wave. We have a much smaller wavelength. That usually results in a much higher frequency, and that is related to higher energy. So a wave that has a very small wavelength, very high frequency, is moving pretty fast. It's got a lot of energy associated with it. You can think of a longer wave just kind of moving itself through space nice and slow, while something that has a very short wavelength is just can kind of keep going really, really fast and have a lot of energy associated with it. We see that even with colors here. Here it's actually 3 waves. You could sort of see it with the sun coming through. 3 colors. We have our red, our green here, and our blue sort of wavelength. And you can see here the red wavelength is much larger than the green, right? And even larger than the blue. So in terms of energy, we would expect red to be more low in energy, right? While here on the blue side would be a much higher energy associated with that blue wavelength, because again, it has a shorter wavelength, a much higher frequency. It's essentially moving through space a lot faster in a sense, right? It's kind of moving really quick rather than the other one that's just kind of moving through space at a much lower frequency. So when we talk about these electrons sort of transitioning from one energy level to the next, and again, releasing that energy as it goes through, it will fall somewhere here on the electromagnetic spectrum. And there's different parts to the electromagnetic spectrum. Down over here, this is a much longer wavelength. On this end is 10 to the minus 12, which is a much smaller wavelength. That means on this end of the longer wavelength, we would expect to be a little bit lower in energy, right? On this end, we would expect it to be higher in energy as we kind of go that way. So down here we have things like radio waves when we listen to the radio and all that kind of stuff. Not too bad on the drive in. As we go to the left there, we have microwaves. We now gain a little bit more energy, enough energy to make the water molecules move really fast in your food and cook it really quickly. Next, we go to the infrared part of the spectrum, and that is where we kind of feel heat and energy sort of given off. After that, a little bit shorter of a wavelength is the visible part of the spectrum. So that is the visible part of the spectrum. That is where we see colors. That is our classic Roy, G, and Biv sort of coming this way, right? That way. So as you can see there, even again, our colors have that difference in energy. So something given off a red light means that that wavelength has a longer wavelength and something is given off more of a blue or violet type of light that is coming off. Usually these guys are given in nanometers. After that is ultraviolet, UV light, right? Which is why we put sunblock on, right? So we don't get too toasty out there and sunburnt. X-rays have a little more energy. Also why they give you a lead vest, right? And leave the room when they shoot the X-rays because it's pretty high energy. And gamma rays is pure energy, radioactive particles, basically very, very high in energy. So you do need to know the different parts here of the electromagnetic spectrum. You need to know them, not exactly where they break off in terms of numbers, but you need to be able to put them in order, maybe from longest wavelengths to shortest, highest energy to lowest energy, lower frequency to higher frequency, that sort of thing. That also includes the colors. You need to be able to put those in order as well, of energy, wavelength, and so forth. Any questions on that there? That's a pickle. Good talk. So as we talk about these electrons that are transitioning from one energy level to the next, there is a certain idea of how these electrons gain energy and lose energy. And this is what is sometimes referred to as a quanta of energy or a packet of energy. So when we think about quantized energy and how electrons gain that quantized energy, it's sort of this idea. For example, you will have an electron that's maybe transferring different energy levels, but that electron will gain enough energy to fully transition from one energy level to the next, or it may come back down from one energy level to the next. It will lose a certain amount of energy to do that. It will not find itself like halfway there and go, I'm kind of good. I'm just going to kind of hang out in between energy levels or something like that. So this idea of quantized energy is that it will gain or lose enough energy to fully sort of transition from one energy level to the next, either upwards or downwards. Sometimes it's compared to like stairs, right? When you walk stairs, you have enough energy to get to this step, to this step, to that step. Again, you don't get halfway through the step, hopefully, and decide, I'll just try to stay here, right? Because you're going to fall. So that's the idea of quantized energy. You have enough energy to move from one step to the next. Electrons move from one energy level to the next. They gain or lose only a certain amount of energy to allow them to do those transitions. Just like somebody walking stairs, right? Some people can only maybe transition one stair at a time, right? Somebody else could come and do two at a time or something like that, or maybe three at a time. So electrons are the same idea. Different electrons can get enough energy to transition multiple energy levels, either upwards or downwards. If electrons gain energy to go upwards, that's an endothermic process, right? In terms of the atom, right? It's absorbing all that energy. And then as they release that energy back down, it's an exothermic process to allow those electrons to come back down. Now, energy is quantized, and radiation is basically particles that are photons, which again is how really the atom releases that energy to allow those electrons to transition down. So as that electron again is making this downward transition, the atom as a whole again has to release a photon, basically of light, that has a specific wavelength that corresponds to it. and also a specific amount of energy that will correspond to that wave that is being released by the atom. And those are referred to as photons. Now, there is a way to calculate the energy associated with that of a photon of light or a wave, and that is the energy is equal to h times the frequency. That is what should be here. There we go. And h is Planck's constant. And Planck's constant is 6.63 times 10 to the minus 34 joules times seconds. Obviously here, that is our frequency. Now, since our earlier equation, which is C is equal to the wavelength times the frequency, we could solve for the frequency, which is C divided by the wavelength, which means if we take that and substitute that into the frequency, we get that the energy is equal to h times the frequency, which is hc divided by the wavelength. This means two things. If you know the frequency of light that you are talking about, you could calculate the energy associated with it. And frankly, if you just simply know the wavelength, you can calculate the energy associated with it, as h is Planck's constant and c is still the same speed of light that we used earlier, 3 times 10 to the 8 meters per second. So if you know either the wavelength or the frequency of the photon of light that's coming off, you could basically calculate the energy associated with that wavelength of light that's coming off. Any questions on that? Here, the wavelength would be in meters again, so that it would cancel out with C. And again, the frequency is reciprocal seconds, which means that you will end up with joules when you multiply the frequency times Planck's constant. Typically speaking, if it is a process where, it's being released by the atom, exothermic, you will probably end up with an energy value sometimes that are negative. And if it's a very positive sort of process where it is absorbing energy, that energy value will be a positive number. So if you calculate energy here, and we're going to do some calculations maybe today and tomorrow or next time that involve energy, you do want to definitely, whenever you calculate energy, you should always keep the correct sign that's there. So if it is negative, it's negative for a reason. If you did the calculation correctly, it's negative because it's exothermic and energy is being given off. So you should keep the negative. And if it's a positive value that you get for energy, then it's going to probably maybe be endothermic. When you calculate things like wavelength or frequency, those things should always be positive numbers. So even if you need to use an energy value that's negative, you would make it positive for that calculation. So whenever you calculate wavelength, frequency should end up positive numbers, but energy can be positive or negative depending on the situation that's occurring. Any questions on that there? All right. We'll go for a couple more minutes, I think. Still be relatable to our lab today, I think. So when we talk about light and photons, there was a lot of experiments, especially one also done by Einstein, which is E equals mc squared. That's the Einstein equation. That is energy, mass, and the speed of light, which is the C there. But there's always this idea of the dual nature of light, and that means that particles like electrons and protons and all those type of things, they can have wave-like functions, so they could kind of travel through space as sort of packets of particles and stream of particles. And waves could have particle-like function as well. So sometimes what is referred to as that dual nature of light, that both particles and waves basically can have similar types of properties and how they sort of transfer or move through space. So when we have these electrons that move through space, they will oftentimes give off a spectrum of light. And basically, there's two types of spectrums that we come across. There is a continuous spectrum, which is when white light is passed through a prism. Basically, it's all the wavelengths basically coming out at once. So when we talk about sort of a continuous spectrum, things like the sun give off a continuous spectrum and stuff like that. A line spectrum is more what we see with elements. So when elements are heated or sort of excited, they give off specific line spectrums. And the real difference here is this is really more of a quanta of energy that we see, because these electrons will only transition certain energy levels and gain and lose energy in a certain way. What you end up getting when you excite something like, say, hydrogen, is you will get these specific lines, which is referred to as a line spectrum, at specific wavelengths and specific colors. They are so specific for elements that each element will give off a different line spectrum. So you can sort of identify a particular element by what color lines you see, what wavelengths they're coming off at. And this is the idea of the quantized of energy. Now, something like the sun, which gives off maybe more of a continuous spectrum, you could kind of relate to what we were talking about before with elements. It's more of that staircase quantized sort of version, like things will gain and move as they're walking up steps. And a continuous spectrum, you could kind of think of it like a ramp, right? If you're walking up a ramp, you pretty much can stop anywhere along the way, right? You could do every bit of that ramp if you wanted to going up there. You could hit every single spot. And that's sort of the idea of continuous spectrum. Pretty much everything sort of coming off at once. They're not just going to transition from A to B, like you see more in a quantized version of energy, which is what we see with elements. Any questions on that there? So when we do that, we do see this emission spectrum happening like we're going to look at today in lab. So this will be kind of like the pre-lab talk right now, I suppose. So when we do excite an electron or the atom, all the electrons in a lamp, when we run electrical current through it, we'll send it through a prism and it will separate out again into that sort of line spectrum. And as you can see here, we see these distinct lines happening at distinct wavelengths based on the transition of those electrons that are occurring. And even the colors that we see will also tell us, you know, again, how many energy levels maybe is traveling, right? So something in a red sort of line that you see could be a result of a transition from a one wavelength, one energy level to the next, not a very big jump in energy between them. Something maybe that's more of a purple or blue line that you see is going to be a result of a much bigger transition from an energy level to the next, which is going to require you to absorb or release a certain amount of energy to do so. So,
when the light emitted,
as you can see here,
charged passed through a prism, a line spectrum results. This line spectrum consists of light at only 4 wavelengths in the visible region.
so that's sort of what you're going to see in lab today. When you look through the spectroscope, you have a prism in there. It's going to separate the light in. When you look at these lights of these different elements, you'll be able to see these distinct lines, hopefully happening as you do it. And these 4 lines that we see in hydrogen here is a result of those electrons transitioning from the different energy levels. All right, so I think we'll lay it up there. We'll talk a little bit more about this in lab in just a bit. Any questions on any of that there? Okay. This